This video explains how you propagate uncertainties through an equation. In other words, if you did an experiment and you took some measurements, then all of your measured values are going to have uncertainties. If you do a calculation using those values, it's not enough to just calculate the answer. You also have to calculate an uncertainty on that answer. This video is going to show you how to do that. The rules for propagating uncertainties are listed in your lab manual, but I'm going to go over all of these with you. To begin with, here's some notation. So when you've got a measurement, it might be 5.7 plus or minus 0.1 meters. The notation that they use in the lab manual would be that the variable a represents your number, and its uncertainty is listed as delta a. So even though that's two symbols, it just means one thing. It means the uncertainty of the value. Now this uncertainty here, this is what's called an absolute uncertainty, meaning it's got units. In fact, it's got the same units, meters, as the value does. So both the value and its absolute uncertainty have the same units. There's also something called a fractional uncertainty, which would just be the absolute uncertainty divided by the value. And notice that the units cancel out, so you wind up with just a pure number. There's also something called a fractional uncertainty, which is just this number times 100 to make it a percentage. We don't use this very much. Mostly we're going to be using fractional uncertainties and the absolute uncertainties. Now the first rule for propagating uncertainties is for addition-subtraction. So the example that they give in the lab manual is A plus B minus C. So you've got three variables. Those are measured values that have uncertainties, and you want to figure out not just what the answer to this is, but also what the uncertainty of it is. So you want the uncertainty of this expression. So the rule for addition-subtraction is that the uncertainty of this expression would be, first of all, you take the absolute uncertainties, you square them, you add them together, and then you square root them. Now, if you're wondering why it looks like this is basically Pythagoras' theorem in uncertainty space. You don't really need to understand that, but the reason why it looks like this is that you're essentially finding the length of a vector. So an example of where you might use something like this would be if you had a glider on an air track and you knew its final position and its initial position, and you wanted to know the total distance that it had traveled. So distance d would be position 2 minus position 1. So position 2 and position 1, those would be measured values. They would have uncertainties. So the uncertainty of this would be, using the rule above, the uncertainty of d would be equal to square root absolute uncertainty of P2 squared plus absolute uncertainty of P1 squared. And notice that it doesn't matter whether you're adding or subtracting these values, you're always going to add the absolute uncertainties. Again, it's Pythagoras' theorem. You're trying to find the absolute magnitude of a vector. The rule for multiplication and division, say you've got three values, a times b divided by c. The rule for getting the uncertainty of this looks as follows. Instead of using the absolute uncertainties, in this case, you're going to use the fractional uncertainties. So it'll be delta A over A, and delta B over B, and delta C over C. Then you square them. Then you add them together. You square root them. And then, because these are fractional uncertainties, we still need to scale it to put the units back on. So you multiply everything by the final answer. So an example of this would be, say you were calculating the speed of your glider. So it's just going to be the distance divided by the time. So this is a multiplication division rule. And the uncertainty of this would therefore be final answer times big square root. And then you'd have the fractional uncertainty of d and the fractional uncertainty of t. And they'd be squared and added together. So again, final answer here and here, and then the fractional uncertainties squared, added together, and then square rooted. The rule for constants is basically that you just treat them like any other variable, except that you set their uncertainty to 0. So for example, say I've got some constant, which has no uncertainty on it, multiplied by a measured value that does have an uncertainty. So A has an uncertainty and K is an exact number. So the uncertainty of this expression, I'm just going to work it out using the multiplication division rule we just saw. So for the multiplication division rule, it would be final answer times square root, and then I'd have the fractional uncertainties of these two things squared and then added together. And now that I've gotten to this point, I can say, okay, K is an exact number. The uncertainty of that is 0. So that goes to 0, which then gives me Ka square root of a square, which is exactly the same thing as saying Ka times absolute value of delta A over A. You notice we have a cancellation here, and I just wind up with a very simple form, K times the uncertainty of the value. Now, if you want to, you can just memorize that you can go directly from here to here and say that the uncertainty of a constant times the value is just going to be that constant times the uncertainty of the value. So you can just skip straight over here, but what I want you to understand is that you can just work it out as if K was another variable and then set its uncertainty to 0 later, and everything will work out fine. The next rule for propagating uncertainties is the roots and powers rule. So say you've got some value and it's raised to the power of a constant. So this could be a squared or a to the negative 1/3, for example. So the rule for roots and powers to get the uncertainty is that you take the final answer and you multiply it by the exponent, so the thing that it's being raised to the power of, and then you multiply it by the fractional uncertainty of the value. And then all of this is supposed to be squared and then square rooted, which means that it's basically the same as absolute value brackets. So final answer times the exponent times the fractional uncertainty, all of it inside absolute value brackets, which basically means that if K happens to be a negative value, you ignore the minus sign. So uncertainties are always plus or minus, so we can just get rid of the minus signs. So we use this one quite a bit. So let me give you an example of this. Say you've got an expression 1 over the square root of some measured value that has an uncertainty, and you need the uncertainty on your answer. So you want the uncertainty of this, and the thing here to notice is that 1 over the square root of a is basically the same thing as a raised to the power of negative 1/2. So now you can just apply the roots and powers rule above. So our value is a to the negative 1/2. That means our uncertainty is going to be final answer, a to the negative 1/2 times negative 1/2 times delta A over A. And then we put absolute value brackets around it, which basically just means we're going to ignore that minus sign. The next rule is for trigonometric functions. So say, for example, you've got sine theta, and you need to find the uncertainty of that. So the rules for this are given in the lab manual. This one works out to be cosine theta times the uncertainty of theta. So that's the uncertainty of your angle, and then all of it inside absolute value brackets. The uncertainty for a cosine, again, following the rules in your manual, is going to be sine theta times the uncertainty of theta, absolute value brackets, and for a tangent, it works out to be the uncertainty of the angle divided by cosine squared, theta, inside absolute value brackets. Now you can just apply these rules, but one thing that's important to remember is that when you do this, the uncertainty has to be in radians. It must be converted into radians or this won't work. So if you had 5 degrees plus or minus 1 degree, you'd need to convert that 1 degree into radians. Following along in your lab manual with the rules, if you've got an exponential, so e raised to the power of some value that has an uncertainty, the uncertainty of that, of your final answer, is just going to work out to be the final answer times the uncertainty of your value inside absolute value brackets. If you've got a logarithm of some value, the uncertainty of that winds up being just the fractional uncertainty. If you're averaging values together, so say for example, the value you want is going to be an average of a whole bunch of values. So A1 plus A2 plus unknown number up to AN, all divided by n to make it an average. The uncertainty you're going to use for this is actually going to be what's called a statistical uncertainty, which means that what you're going to calculate is 2 times the standard deviation divided by square root n, where n is the total number of things that you average together. So this squiggly symbol that I've written here, sigma, draw that carefully, it's called the standard deviation. And if you look in the lab manual, they give you a formula for it, but it's quite ugly looking, and luckily you never have to calculate it yourself. In this course, you're always just going to get it either from your calculator or more likely from Excel. So an example of when you would use something like this would be, for example, if you were timing a glider on an air track and you were going to time it 20 times and then average all those times together, you'd use this formula here to calculate the uncertainty on the average time. So another thing I want to point out here is, say you've measured a time in your experiment and you have an uncertainty for it. So say, for example, you measured a time with a stopwatch, and then this would be the uncertainty of the stopwatch. Or maybe you measured a time with a photo gate, and this would be the uncertainty of the photo gate. This absolute uncertainty here is a completely different number than the statistical uncertainty over here. They're not related to each other at all. And in fact, the reason why we average values together is so that we can get the statistical uncertainty, because it gets smaller when n gets bigger. This part of the video shows you how to deal with a complicated expression, one where you need to apply several of those uncertainty propagation rules. So for example, say you've got an equation like this, and A, B, D, and F, those are all measured values. They all have uncertainties. And the question is, where do you start with this? Because we've got one little section here where you would apply the roots and powers rule, another little section here where you would apply the addition-subtraction rule, and another little bit here where you would apply the exponential rule. And then, of course, the whole expression is going to involve the multiplication-division rule also. So we've got 4 different rules we need to apply. Where do we start? Well, the first thing you're going to do is you're going to identify little pieces of this equation where you only need to apply one of the uncertainty propagation rules. And in fact, that's what I showed you before. So this little piece of the equation, you only need to apply the roots and powers rule. And in this little piece of the equation, you only need to apply the addition-subtraction rule. And in this one, you only need to apply the exponential rule. Now, in the manual, they suggest that you actually make substitutions. So you would say d squared is equal to p, and a plus b is equal to q, and e to the f is equal to r. So they suggest starting it this way, where you make a substitution for each of those little bits. I'm not actually going to do that. I'm instead going to treat each of these little bits as a black box. So I'm just going to use these symbols, but I'll treat it as a box. I'll pretend I don't know what's inside the box. So looking at this expression, you can see that we've got box times box divided by box. So that would just be the multiplication division rule. And so that's what I'm going to start with. I'm going to write down what the uncertainty of this expression would be if I just treat it as 3 things that are multiplied or divided together. So the multiplication division rule says that the uncertainty of this equation here is going to be equal to final answer times a square root, and inside it, you're going to have the fractional uncertainties of each of these 3 blocks squared and added together. So let me do that now. So the first box, we have the uncertainty of d squared divided by d squared. And then all of that gets squared. Then we'll have the fractional uncertainty of the next term, uncertainty of a plus b divided by a plus b. So note, I'm not worrying about what's inside the box, I'm just writing it down. So uncertainty of a plus b divided by a plus b. I'm basically pretending I don't know what's going on inside that box. And then the third term is going to be the uncertainty of e to the f divided by e to the f. So the next thing to realize is that I don't actually know what the uncertainty of d squared is yet. I have to figure that out and then nest it into this equation. Likewise, I don't know what the uncertainty of a plus b is, and I don't know what the uncertainty of e to the f is. So that's my next step, is I have to figure out what these uncertainties are and then nest them into my equation. So let's do that now. If your expression is d squared, then the uncertainty for that uses the roots and powers rule, and that would just give me final answer times the exponent times the fractional uncertainty. And if my expression is a plus b, then the uncertainty of that, according to the addition-subtraction rule, would be square root, and then the absolute uncertainty of a squared and the absolute uncertainty of b squared. And if the equation is e to the f, then the uncertainty of that is just going to be final answer times the absolute uncertainty of f. So these three equations are the things that we're going to then nest into our equation down here. So let me now write that down. So the uncertainty of the expression will be final answer, which is just d squared times a plus b divided by e to the f, big square root. And now we're going to nest our solutions in here. So the uncertainty of this d squared we found up here. So I'll put that in now. So I'll have d squared times 2 times delta d over d on the top. And all of that gets divided by d squared, like I have here. And then that's all squared. Then we put in the next term. So the uncertainty of a plus b we found here. So I'll put that in now. So square root delta a squared plus delta b squared. And then all of that divided by a plus b, just like I have here, all squared. And finally, third term, we put this uncertainty in on the top. So e to the f delta f divided by e to the f, all squared. And all of that's inside this square root. Now there are a few cancellations you can make here, but even if you didn't, this would be your complete expression. So this is the uncertainty for this expression. If you're still having trouble with this, do ask your lab instructor for help. Propagating uncertainties is probably the most difficult thing that you learn in the labs, so your lab instructor is expecting to get questions about it. Don't be shy.